In this video, we're going to go over solving linear inequalities, and there's two types of linear inequalities we can solve. When you have a two-variable linear inequality, it's when x and y are both in the inequality. So this is no longer an equation because we don't have an equal sign. This time we have an inequality symbol. Your inequality symbols are greater than or equal to, less than or equal to. So the solution, when you have a two-variable inequality, the solution is a solution set. It's all of the ordered pairs, x comma y, that make this inequality true. So all of the x comma y's that will make the left greater than the right. And in order to do this, your solution set, you have to shade the coordinate plane, okay? So the first thing that you do is, okay, you have a two-variable. You need to graph to find what ordered pairs make the left greater than the right, because it says y has to be greater than 2x minus 1. So the first thing you do is you find the boundary. Okay, the boundary is just going to be when the left equals the right. So that's going to be y equals 2x minus 1. So that's what we're going to graph first, the boundary. This is going to separate your answer solution from your non-answer solution. Okay? I should say from the correct side from the incorrect side. So we have to graph this line. So 2x minus, it's got a negative 1 is the intercept. Go up to right 1, up to right 1. But before you do this, the boundary is either part of the solution or it's not part of the solution. If it's part of the solution, your boundary should be solid. If it's not part of the solution, then your boundary needs to be dashed. So if you look, the line is when the left equals the right. Is the left allowed to equal the right? No, the left has to be greater than the right. So in this case, our boundary for this problem, our boundary should be dashed because this symbol would need to be this symbol or this symbol if it was going to be solid. So what this dash means is this is the boundary, but none of the points on the boundary are part of your solution. If the boundary was solid, then all of the points that fell on the boundary would be part of your solution. So the boundary just separated your plane into what's called a half plane, okay? Two halves, the left, the right. And one of these halves is the solution and the other half is the incorrect answer. And the only way to figure it out is you need to test a point from one of the sides. You cannot test a point that's on the boundary. So you have to pick a point that's 100%, you know for sure, not on the boundary. So I know, I'm 100% confident, 1, 2, 3, 4, that the point 0, negative 4 is not on the boundary because the y-intercept is 0, negative 1. So what we do is we plug 0 in for x and negative 4 in for y. So negative 4 greater than 2 times 0 minus 1. So is negative 4 greater, 0 minus 1? Is negative 4 greater than negative 1? Is this a true statement or a false statement? This is a false statement. And the point, okay, the point is to the right-hand side of the boundary. So if that point is to the right-hand side and it's false, that means that this entire side would be false answers. That means the entire side on the other side is true. So your solution would be every single coordinate point on the left side of the boundary. So any coordinate point that's on the true side is a solution. So if you test a point and it's false, okay, here's my point. That means this entire side is false. That means the other side is true, and you always shade the true side. So this is a two-variable inequality. Now let's talk about a one-variable. So if you have a 1 variable, it looks something like this. 2x plus 1 is less than 5. Okay, notice you don't have x's and y's, you just have x's. So instead of being on a coordinate plane, okay, your solution goes on a number line this time because it's 1 dimension, okay? It's going to be the range of x values that makes this true. So we have to make sure that 2x plus 1 is less than 5. So we would take away 1 from both sides. That's going to give us 2x is less than 4. Divide by 2 because we're trying to get x by itself, so we would get x is less than 2. So as long as we plug in a value where x is less than 2, it will make 2x plus 1 less than 5. And we can show our answer on a number line. 2, 3, 1. Now, can x be 2? No, it can't. But it can be anything less than 2. So on a number line, the way you show that it can be infinitely close to 2, but it can't be 2 is when you do an open circle. And then it says less, so we would shade to the left on the number line. And we would put our arrow. Okay, so that was number 1. Why don't we solve the next one? Why don't we do negative 3x plus 4 is greater than or equal to x minus 8. Okay, so actually let's change it a little bit. Let's put a less than or equal to sign there. Okay, so the first thing is, I can't have x's on both sides of the equation. So I'm going to take away x from both sides. That's going to give me negative 4x plus 4 is less than or equal to negative 8. So now I want x by itself. So I'm going to take away 4, just like an equation. Negative 4x is less than or equal to negative 8 minus 4 is negative 12. But here is the part that's different. When we have to divide by a negative. When you divide or multiply by a negative, the symbol flips. The symbol flips. Inequality symbol flips. So this is now x is less than or equal to negative 12 divided by negative 4 is 3. So that is our solution. It's now x is greater than or equal to 3. So on a number line, okay, 3, our solution is allowed to be 3. So on a number line, we shade in 3 and then go to the right. Anything to the right and 3 is a solution, okay? So when it's a 2 variable, okay, the boundary is dashed when it can't be, but when it can be, it's solid. On a number line, when it can't be that boundary of 2, it's open circle. When it can be the boundary of 3, closed circle. Okay, now we're going to go over something called a compound linear inequality. It's when you have 2 or more inequalities in the same statement. Now you have 2 types of compound linear inequalities. You have an and you have an or. Now, one is more restricting than the other. If I said that the only way that you can graduate high school is if you got an SAT score of 1600 and you got at least a B on every single subject. And means you have to satisfy both of those conditions in order to graduate. If I said you have to get a 1600 on your SAT or you have to get above a B on all of your subjects in high school to graduate, you only have to satisfy one of them in order to graduate. So an and is more restricting than an or. So for an example, if I said that 2x plus 1 is less than, let's say, 9, and x plus 2 is greater than or equal to 3. Okay? What we do when we have an and or an or, we're actually going to end up using 3 number lines here. Okay? We're going to solve each of them separately. So we're going to take away 1, and we get 2x is less than 8. Divide by 2, and we get x is less than 4. And take away 2, we get x has to be greater than or equal to 1. So we have to satisfy both of these to be the solution. This right here is the problem. This is called a compound linear inequality. You have 2 inequality in the same statement, and it's an and. So what you do is, okay, 1 and 4. So I'm going to put a 1 here, I'm going to put a 4 here, I'm going to put a 1 here, I'm going to put a 4 here, a 1, and a 4. Now, I'm going to graph each of these separately on number lines, okay? So x is less than 4 would look like this, okay? X is greater than or equal to 1 would look like this. Now, if it's an and, it has to satisfy both of these conditions in order to be the solution to the final problem. So we're going to visualize this, okay? Everywhere to the left of 1, is this covered on both of the number lines? No, only the first number line has solutions less than 1. Okay, what about 1? Is 1 on both of the number lines? Yes. How about between 1 and 4? Is between 1 and 4 on both of the number lines? Yes. Is 4 on both of the number lines? No, but that's where our little range of solutions lasts. And then, is anything greater than 4 on both? No. So where do they share? Well, they share 1, and they both have everywhere between 1 and 4, but then it stops when x is 4. So this would be the solution, okay? This would be the number line solution, and this would be our solution. X has to be less than 4, and it has to be greater than or equal to 1. So 5 does not work because 5 is greater than or equal to 1, but it's not less than 4. So this right here shows you all of the answers. Okay, 1.7 works, 3.5 works, 3.999 works, okay? But 0 does not work, 5 does not work. For an or, if you had 2x plus 1 is greater than 9, or x plus 3 is less than 2, okay? Or, okay, it's least restricting, okay? Or I should say it's less restricting because there's only 2 options here. So we solve each of them separately. So we take away 1, and 2x is greater than 8. Divide by 2, we get x is greater than 4. Or take away 3, and we get x is less than -1. Okay, now it only has to be one of these to be true. So if you have, and we're going to draw 3 number lines when we have compound inequalities. We put these numbers, always put the smaller number to the left, bigger number to the right, smaller number to the left. That's how a number line works. Bigger number to the right. Okay, graph each of them separately. X is greater than 4. Open circle to the right. Open circle to the left. Now, as long as it's on one of the number lines, then it's a solution when it's an or. So all we're going to do is, we're going to just copy everything we have here as our final solution. So x is less than or equal to, x is less than -1, or x is greater than 4. It does not matter. Okay? You just copy everything you have because as long as it's on one, it's on the final answer for an or. Okay? So as long as you're greater than 4 or you're less than -1, you're a solution to this entire compound inequality. Okay? So what that means is, if I was the value of -27, even though that's not greater than 4 since it's less than -1, it's a solution to this inequality here. Okay, so that's it for compound inequalities. We have compound linear inequalities. You have two options. It's either an and or it's an or. The and is more restricting than the or.